chapter is bonding, part 1. And the next chapter will be bonding, part 2. And so this is the second to last chapter. And we're going to do what's called the Lewis theory of bonding in this chapter. So if you learned this already, in high school, you'll see a lot of similarities. Okay, basically what Lewis theory says is that noble gas configuration is desired. So everything likes to have a noble gas configuration. That's what Lewis is built on. And it also, so it says a couple things. You'll see this in your reader. You follow along there. What bonds is the valence electrons, not the core electrons? How do you know what's a valence electron, what's a core electron? Well, for example, for, say, beryllium, I'll put this example over here. For beryllium, you would write helium 2s2. Everything that's in the brackets, in this case for helium, is considered a core electron. It's close to the center. Everything not in the brackets, we consider a valence electron. So what Lewis says is only valence electrons are involved in bonding, which would be the ones on the right. Okay, so that's the helpfulness of writing shorthand, is everything in brackets is core. Okay, there's two types of bondings we're going to talk about a little bit, ionic and covalent. So I'll mention those a little bit. And then there's something called the octet rule. Octet is another way to say noble gas configuration. Octet meaning 8, and here's why they use that word. If you look at the lithium row, it's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, 8. So that's going to be 8 electrons in the valence shell. Same is true for the sodium row, or really any other row if you're not including the transition metals. So there's 8 if you add up the 2 from the S block and the 6 from the P block, or the P electrons. So that's where the word octet comes from. Octet again means really noble gas configuration. Okay, and so in this section we're going to use something called a Lewis symbol. You'll see it at least once in a while. Lewis symbol. The Lewis symbol is nice because it indicates valence electrons. Let me show you a picture. Something like this is in the reader and the textbook. In group 1A, so we're looking at the A rows, if you look on the ones on the wall, the A columns, I should say, are the ones we're focusing in on for Lewis structures. We're not going to do Lewis structures of transition metals in our class. So, group 1A, the way you know the number of valence electrons is by the group number. So 1A, thus 1, has 1 valence electron. 2A will have 2. And so you draw the valence electrons by putting dots around the atom or element. So 2A, you see 2 dots. 3A, the boron, aluminum, you see 3 dots. Group 4A, and it's like you're putting them around a box, as you can see in the picture. They're just going around the box. So there's 4 sides of a box, imaginary box surrounding the element. Once you get to group 5, since you have 5 electrons, that would be the nitrogen column, you're going to start pairing those electrons. And in this picture, the electrons for nitrogen and phosphorus are paired on the left side. That's totally random. You could have put the pair on the top, the right, or the bottom. It does not matter where the pair goes. In group 6A, you see now 2 pairs of electrons. In this case, the top and the left. Again, that's random. You could put the pairs on any one of the 4 sides. And then there's group 7A, and then finally 8A, the noble gas configuration. That has an option, and you'll see 8 electrons around the atom. So these are called Lewis symbols. You should be able to generate a Lewis symbol for really any element we give you. Okay, a simple way then to make a Lewis structure, which is a structure of a molecule, is just to combine the symbols. We're not going to end up doing this later, but as an early illustration, it's kind of nice to look at. Let's say we took potassium, and let's take another color here, chlorine. So chlorine has 7 dots around it, potassium only has 1. And what's going to happen is, these 2 electrons here are going to mate and form a bond, okay? And it will look like following. Okay? It'll look like the following. Potassium chloride. But in this case, the chlorine needs all 8 electrons, but the potassium actually wants to lose its electron to become a noble gas configuration. If you look at the periodic table, it needs to lose 1 electron to become K+. So it's actually not going to keep those electrons. The potassium is going to give its electron away, and the chlorine is going to keep it. So what you would have, I'll just put brackets around this, a plus charge, and this is a minus charge. And we call this ionic bonding, or a transfer of electrons. So whenever there's a transfer of electrons, that's ionic. In contrast, let's do this one now. Let's go H dot plus, and we'll do chlorine again. 7 dots around it. It's in the 7th column. This will form H and Cl. In this case, if the hydrogen, it's a nonmetal, remember, it wants to add an electron to be like helium. So its noble gas configuration actually only has 2 electrons, be like helium, and then chlorine wants to be like argon. So it needs 8 electrons for itself. So in this case, they're going to share those 2 electrons. This is called a covalent bond, where the electrons are shared between the 2, so they're both receiving the positive benefits from both electrons. Okay? And both electrons are allowing them to have, I'll put in quotes, an octet, or really a noble gas configuration. And these here on the right would be called Lewis structures. Or some people will say Lewis formulas, but I'll use the term structures, Lewis structures. Okay? So you'll need to be able to generate Lewis structures. In the beginning, they'll be super easy. As we go on, you'll see they can definitely get tougher. All right, we're going to section 9.2 and 9.3 right now. You're going to do them both together. And this is types of bonds. Types of bonds. Okay? And in the reader, this is, again, page 83 and following. In the textbook, we're somewhere, page 348 and following. Okay, we're going to learn 5 types of bonds, of which you need to know all of them. Some will be more relevant for us, some will be less. Type 1, we already learned it, ionic. This is between a metal and a non-metal. So you need a metal and a non-metal. Which one's ionized, metal or non-metal? Which one do we ionize electron? From the last chapter. The metal is ionized. It wants to lose an electron to have its noble gas configuration. This undergoes electron affinity energy to gain an electron. So it transfers from the metal to the non-metal. So electron transfer, transfer is the key word, goes from the metal to the non-metal. At least one, maybe more. Okay, that's the first one. Number 2, Ray heard this word too, covalent. This is where there's no exchange. The key word is sharing. Sharing of electrons. And here you need 2 nonmetals to make this happen. 2 nonmetals. Where in this case we share, and the example was HCl that you saw earlier, those were both 2 nonmetals. They share the electrons. Okay. all from number 2, which is this one, through number 5, they're all covalent types of bonds. Okay? This was just a pure covalent, your typical covalent bond. The next one, number 3, is a coordinate covalent bond. Coordinate covalent bond. Okay? Here, both the electrons are still shared, but in contrast to the previous, where each brings one electron, in the coordinate covalent bond, one atom brings both electrons to share. Okay, so you got the rich friend going to the poor friend's house. The rich friend brings all the electrons over. Okay, so I'll do this example. I'm going to draw out the Lewis structure here. You probably don't know how to do this yet, which is fine. I will just show you what it would look like. Later in the chapter, you're going to learn how to do these. Sulfate, what does the Lewis structure look like? It looks like this. If you know how to do this already, that's fantastic. Okay, there's a sulfate. It could be made to look a little bit better, but that'll do for us. How about a sulfite? What does that look like? It looks like this. Kind of similar, but there's only 3 oxygens on it. And then that oxygen, let's draw the Lewis symbol for it. Look like that. All right, now let me get a different color. In this case, see how this oxygen here on the left-hand side, this one right here, has 6 electrons around it and 1 bond. Okay, if you didn't know, 1 bond means 2 electrons. So if you see a single bond like that in this case, that means 2 electrons. So this oxygen right there, it's underlined, has 6 electrons, and over here, it still has those 6 electrons. Okay? Where did the bond come from? Well, this bond right here that I just circled came from these 2 electrons on the sulfur right there. Okay? So all the electrons are contributed by the sulfur, but the sulfur and the oxygen equally share them when they make the sulfate. Okay? So this is a coordinate covalent bond, and often a coordinate covalent bond will be between an oxygen atom and another nonmetal. Typically, those will be coordinate covalent bonds. Okay, number 4. Multiple covalent bonds. Multiple covalent bonds. Let's do an example. Again, I'm going to draw a Lewis structure. I know you haven't learned how to do this yet. That's okay. I'm going to do it for carbon monoxide. Carbon monoxide. It would look like this. There's different ways you could draw this. I will just draw it like this for now. I need to put 4 electrons between carbon and oxygen for them to have an octet. Or I could do it a different way, and I could put 6 electrons between carbon and oxygen. Again, so they both have an octet. Let's check the octet, and you'll see how this will work. An octet means each atom must have 8 electrons. Let's look at the carbon in the first picture. In this case, it's not as great. 2, 4, 6. So that's not quite an octet, but it does, we're forming a double bond. The oxygen has 2, 4, 6, 8. That's good. So I changed this to make it a triple bond. It's even better now, because notice the carbon has 2, and then each bond is 2, 4, 6, 8. And the oxygen has 2, 4, 6, 8. So the right-hand case is what we call a multiple covalent bond or a triple bond. This would be a double bond. The picture on the right is better, but at least this illustrates different kinds of bonds besides single bonds. So you can have more than a double or triple bond, or you can have more than a single bond. You can have double and triple bonds. Can you have more than triple bonds? We won't see them, but yeah, with metals, with certain atoms, you could go up to quintuple bonds. Yeah, that would be 5, quintuple. And maybe more. We'll see what the research kind of pans out as time goes on. Number 5, here's the last one. Number 5. Polar covalent bonds. Polar covalent bonds. This is when electrons are shared, but they're not shared equally. So when my son's friends come over, and my son shares his toys, but not totally. They can look at the toy, maybe touch it, but they can't totally play with it. That's a polar covalent bond. And so let's, for example, take a look at bromine. This would be the Lewis structure for Br2. Or if you look at H2, this would be the Lewis structure for H2. And I'm going to draw bubbles around them representing the locations of the electrons. What's bigger, bromine or hydrogen? Bromine's definitely bigger. It's lower down on the periodic table. Hydrogen has very few electrons. I'm going to draw a very small little bubble. Again, these bubbles represent the location of the electrons, or the radius, essentially. So the bigger bubbles are going for bromine because it's a bigger atom. Hydrogen is much smaller, so we draw very small little clouds or bubbles around them. Now, if we form HBr, this would be the Lewis structure of it. And if I draw the size here, hydrogen would have to be very small and bromine would be very big. And basically what's happening is bromine, not with itself, but when it gets with hydrogen, it will pull the electron density towards itself, making its size bigger, or more electrons closer to it than is closer to hydrogen. So it's not going to share, this bond here in the third case is not shared equally. This we call a polar covalent bond, not equally shared. So these would be polar. This would be non-polar bonds, non-polar covalent bonds. And we're going to see these terms at the end of the chapter again. Polar means an unequal distribution. Non-polar means an equal distribution of electrons. Okay? So these bubbles are not equal in size. The bromine's it's more than its share of electrons, so this is polar. How do you know if something's polar? Oh, joy of joys, by the electronegativity we just learned earlier. Remember, electronegativity goes between what two numbers? 0 and 4. If it's between 0 and 1, what do we call it typically? Covalent. Between 0 and 1. Between 2 and 4, we called it ionic. And what's between, it's really a continuum. And so something can be perfectly ionic if it's around 0. And then it's polar covalent, or perfectly, I should say, covalent if it's at 0. And then becomes more ionic over time or less covalent. So the middle region is called polar covalent. We might say that more specifically between 1 and 2 is polar covalent. On that graph, and if you got the graph, it was earlier in your notes when we did that. Let me see if I can find it again. This is the graph I'm talking about, right there. We got the covalent, we got the ionic. Polar covalent would be in this section here in the middle. But really, the perfect covalent would be 0 here. And then it becomes more polar as it gets away from that. But generally, anything between 0 and 1 we call covalent. This would be kind of the polar covalent region, and then we have ionic. Okay, how do you find out these numbers, you must be wondering. Maybe you don't care, but you have to, unfortunately. Here's something from your textbook. Electronegativity, remember, increases up and to the right. The most electronegative element would be fluorine. We pay no attention to the noble gases in this case. So electronegativity goes up. So how would you find what the electronegativity of a bond would be. Glad you asked. Let me show you. Oh, by the way, these values will be given on the final if you need them. Okay? So you would have these values. And they'll probably be given on the periodic table themselves, on the back of the final. Okay. Let's do a little example. Let's do KCl. K on the periodic table is 3.0. Oh no, not 3.0, that's chlorine. Chlorine is 3.0. K is 0.8. So I just got that from here. Cl is 3, K is 0.8. How do you find the electronegativity of the bond? All you do is you can go change in electronegativity or just electronegativity is just the absolute value of the difference. The absolute value of the difference. In this case, this would be 2.2. What would we call this? 2.2. Ionic. And it should be ionic. It's a metal and a non-metal. So from what we knew before, it's ionic because there's a metal. Even from chapter 3, we know if there's a metal, we call it ionic. And this is why, because the electronegativity difference is so huge, it'd be an unequal distribution, a huge unequal distribution, where you would transfer the electrons from potassium to chlorine, as we saw when we did that earlier. Let's do another one, HCN, hydrocyanuric acid. We can have two bonds, there's two bonds here. So hydrogen is 2.1. Carbon from that table is 2.5, and nitrogen is 3.0. This again is from this green electronegativity table here. 3, 2.5, and 2.1. So there's two electronegativity differences here. I'll do this one first. Change in electronegativity equals absolute value of 2.5 minus 3.0, or 0.5. And for the other one, I'll do it in a different color. That one, change in electronegativity is absolute value of 2.1 minus 2.5, and that'll be 0.4. Okay, what would we call these? Covalent bonds. They're between 0 and 1. Well, we should have known that even from earlier. If you have two nonmetals together, hydrogen, carbon, and nitrogen are all nonmetals, you're going to form a covalent bond with very little polarity. Okay, so these are not really very polar covalent, slightly polar covalent, but we typically call these just covalent. Okay, so that's how you calculate those differences. On past finals, sometimes we've had people do that, or you can just look at it. Sometimes we've had to calculate the difference. Sometimes we have you just look at it and tell us if it's polar, covalent, or if it's ionic or covalent. Sometimes, and just to go back up to the first example, we'll have you use little symbols, and Greek people will probably like this. What's this letter here? That's a delta, a lowercase delta. We'll try delts or whatever. This is positive, that's negative, okay? Meaning the chlorine's more electronegative than the potassium, and one way to show that if you don't have the numbers is to put the more electronegative one with a delta minus, and the more less electronegative one with a delta plus, okay? So you can show electronegativity with symbols if you don't have the numbers. And you probably do that a lot more if you take OChem. All right. Section 4 and 5 we're going to do together. Unit structure. This is page 85 in the reader, in the textbook. So we're around 357. All right, what we want to do, what is helpful, is we can draw the structure of a molecule, which is pretty cool because we can know what a molecule would look like by using the method of the Lewis structure and the octet rule and all that sort of stuff. So it's very nice to know what a compound would look like, and Lewis theory gives us a way to do so. And what I'm going to show you here, this is from the reader on page 85, it's also posted on SmartSite, is this is the flow chart I'm going to use to figure out what a Lewis structure would be. Okay? So this is kind of the methodology I would use. I'm going to walk you through it, and then we're going to do some examples. So let's zoom in here. This is how to draw a Lewis structure. First step, find the total number of valence electrons. You're going to count that from the periodic table, knowing the column of something. So for example, if you had iodine, that's in column 7, that would add 7 electrons. Then what you're going to do is draw what I call the structural skeleton, or the backbone of it, based on the elements you have. And you're going to fill in single bonds. Then what you're going to do is use the total number of valence electrons to fill in the rest of the electrons. And what I like to do is start on the outside of the molecule and work my way in. So I do center atoms last. And I do what I call terminal or outermost atoms first. Okay? Those are the easiest, I think, to start with. Now, there can be some issues when you end up having too much valence electrons. I'll talk about that later. Sometimes you're going to end up with too many valence electrons. But what you're going to do, after you fill everything in, you have to double check that everything has an octet. That's 8 electrons around it. If it does, you're good. It's all cool. If all atoms have an octet, your Lewis structure is complete. You can consider something called a resonance structure, which I'll show you in a little bit. Sometimes some atoms won't have an octet. I'll explain this more later, but let me highlight hydrogen. Hydrogen we saw already in HCl. Hydrogen's way over there. How many electrons would hydrogen have to have its noble gas configuration? Just 2. It would be helium, which has 2 electrons. So hydrogen will not have an octet. It will have something like a 2-tet. But that will be totally fine. So not everything has to have precisely an octet. But if you really cannot fix it, not everything has an octet, the way to fix the problem is to make multiple bonds. So make a double bond or a triple bond. And I'll show you how to do that. But that's an easy way to fix the octet issues, is to make double bonds. Okay. So that's a general concept. We're going to follow that flow chart and try some examples. And today we'll try the easier examples. Try SO2. What you're going to do is you start off, you follow the flow chart that I have. Valence electrons is first. So with valence electrons, we have a sulfur in column 6, and we have 2 oxygens in column 6. So this is going to be a total of 18. Now, how do you draw the skeleton? Well, if you have something like this, let me tell you now what this means. This would be a chemical formula. The atom listed first is what we're trying to tell you that's the center atom. And then the list of atoms afterwards, meaning like 2 oxygens or 5 oxygens or whatever, that means those atoms are around the first one listed. Okay? So what this means is sulfur is in the middle, and there's 2 oxygens around it. Okay, so whenever there's a list, that means those atoms are around the other one that's listed. Okay, next what I do is I make single bonds. Okay, between all the atoms, and this is my skeleton. So each bond is 2. So this is 2, 4 of a total of 18 that I need in the end. So 2, 4 of 18. So now, I need to put in the rest of the electrons, the other 14 electrons. So what I'm going to do is start making lone pairs of electrons around the outside atoms. So I just did 2, 4, 6, 8, 10 of 18. Now I'm going to go to the other terminal or outermost atom. See, 2, 4, 6, 8, 10, 12, 14, 16. Okay, now I've done 16 of 18 electrons. My last set of electrons is going to go in the middle. Okay, so I do the middle one last, is what I recommend. And then take a look at this, and you say, what does not have an octet? say it's sulfur. Because sulfur only has 2, 4, 6, where oxygens each have 2, 4, 6, 8, and 2, 4, 6, 8. So sulfur is the only one without an octet. How do you fix that? I will show you with a magic trick. Let's call you Olivia, is that okay? Okay. Pick right or left, what's your favorite? Right, okay. And then pick top, middle, or bottom. Okay. She just randomly, we didn't talk about this ahead of time, pick the one on the right and the electron pair up here. Okay? You can do this at total random. What you're going to do is cross that out, ignore it, erase it if you have an eraser, and make a double bond there. Now, how's the octet? Is it fixed? Yeah, everything has an octet now. I've removed one pair of electrons, and I have an octet now. So I'm good. I'm actually done. I can draw what's called a resonance structure if you had picked the left side. There's another one. Okay? So that's called a resonance structure. And they're considered equivalent in this case. And to show in symbols, so you don't have to write the words resonance structure, you draw an arrow with a double-headed arrow, essentially. And that means, via symbols, resonance structure. Or these two are resonance structures. There's no other resonance structure, and in fact, it doesn't matter which set of electrons Olivia had picked, they all would be the same molecule. But it does matter if the bond is on the right or the left. So the double bond one specifically, if it's on the right or left, that means it's a resonance structure. What's a resonance structure more specifically? That means it's the same structure essentially, but electrons have just moved. So when you move electrons around, in this case from the right to the left, then you've made a resonance structure. Okay. One more thing to toss on to Lewis structures here, and that is the formal charge. You need to calculate this thing called the formal charge. It's sort of similar to an oxidation state, but what we didn't tell you before is oxidation states, when you're calculating those, we're assuming an ionic character. But formal charge assumes covalent, which fits better with Lewis. So we need to calculate something called a formal charge. There's a tricksy way to do it in the textbook, which is on page 362. I'm going to teach you my way of doing it, which is different than the textbook. So I need to warn you ahead of time. I'm teaching you a method that's different from the textbook. Here's how my method works. The formal charge is perfect, or zero, when the number of points of intersection, I'll say, is equal to the column number. So for example, oxygen is column 6. Do you see that? If I come over here, and let's look at this oxygen right here. Notice there's 1, 2, 3, 4, 5, 6. I'm not counting total electrons. I'm just doing a little trick where I count the points of intersection. 1, 2, 3, 4, 5, 6. You see that? This has a formal charge of 0. Check this one out. It's 1, 2, 3, 4, 5, 6, 7. 1 over, 1 extra negative electron. So this has a -1 formal charge. Let's try sulfur. Sulfur is in column 6. It has 1, 2, 3, 4, 5. It's short by 1. It has 1 less electron. This is positive. You can do the same on the top. Sometimes people are stumped a little bit in the beginning, but you do need to get used to this. Now notice, what's the sum of the formal charges in this case? 0, which is equal to the overall charge of the molecule. That's always true. The overall charge is 0. That means the sum of the formal charges better be 0. The perfect formal charge that we love is 0. 0 is an awesome formal charge. We can be okay with plus or minus 1. So this is great. This is fine. It's okay. But anything outside of that is not good. So if you get a formal charge of, say, -2, you have a bad Lewis structure. If you have a formal charge of +2, bad Lewis structure. If you get all zeros, which many Lewis structures are all zeros. If you have to guess a formal charge, I'd always guess 0. But a formal charge of all zeros, you probably have the right Lewis structure. If it has plus and minus ones, like this case, is probably about as good as we'll get. But I will teach you some exceptions next time.